here's the idea with clock, okay? What we're trying to do is approximate aging of the pages for the ones used long ago in history, okay? Every page in this algorithm is going to have a bit called a use bit, okay? When I first have a page fault, and I take a page and I load it into a frame, I set its use bit. I've got a pointer. Except this time the pointer's in here. Initially everybody's 0. And my clock is pointing to there. So when I generate a page fault, I'm going to look to see if the use bit is 0. If it is, I'll set it to 1. Okay? And then, of course, load whatever page, I'll put it to that frame. And increment my pointer. Okay, so when I first go around here, it's pretty easy to understand. Page fault's generated. I need page 4. Use bit was 0. I put 4 in there. I set this to 1. Increment the pointer. Then I need page 6. Use bit was 0, so I put 6 in there. I set the use bit to 1. Increment the pointer. Everybody's happy. 1 gets called. 1's not in a frame, so use bit is set to 0. Put page 1 in there, set its use bit 1, increment the pointer. Then page 3 gets called. Use bit is 0. Does that look like a 3 to you?
No.
Yeah, well, doesn't to me either. Put 3 in there, set the use bit to 1, increment the pointer. Now it gets fine, right? We need page 2. Yes?
What were we using the big one again?
Say again?
What were we using the big one again?
The use bit?
Yeah.
We're still trying to understand this use bit. The only thing we've talked about so far is that, hey, if the use bit is 0, then I can put my page in there to that frame. And when I do that, I'm going to set it to 1 and increment the pointer.
Yes.
That's all I've said so far. But now we've got an interesting situation, right? I need 2. 2 isn't in here. My use bit is 1. So what I do is I age it. I set the use bit to 0, and I increment the pointer. Use bit is 1. I set it to 0, I increment the pointer. Use bit is 1. I set it to 0, I increment the pointer. It's pretty exciting, isn't it?
Yeah.
Use bit is set to 1. It gets much more interesting here real soon. This is the initial conditions. I set it to 0, I increment the pointer. Its use bit is set to 1, I set increment. Decrement it to 0, increment the pointer. It's 0! Yay! And that's the loser. 5 gets kicked out, 2 gets put in there, and I set the bit to 1. And I increment the pointer. Okay? So obviously, if I ask for another page, like 7, it's not in here. Use bit is set to 0, 4 is the loser, 7 comes in here. I set the bit to 1, increment the pointer. 2. Let's say I want to access page 2 next. Okay? Well, I go to page 2. Oh, that was a bad example. Forget 2. 2 was not interesting. Let's say I wanted to access page 3. Okay? Well, I go to 3. I set its bit to 1.
0.
And increment the pointer. This incrementing the pointer is important because whenever I access that page, I want it to be the most recent one. And in a clock scheme, you could always see that pointer minus 1 is the most recent one. So I want to access this one last, right? So if everybody else was set, I don't want to come back to 3 and kick it out because I just accessed it. I might want to access it again because of locality reference, right? So I always want to increment the pointer. And what setting these bits, setting these use bits does is it freshens the life of this page. I just recently used it, right? I want to get rid of these others that haven't been used in a longer time. Even if 3 was here, I would want to skip over it to get to 1 and 6. If 6 was up here and 3 was down here, right? I would want to skip over 3 because I just used it and get rid of one of these older ones first, regardless of whether it comes up first on the next pointer increment or not. Question?
So your pointer was at 6, but then you want to access at 3. You could just go ahead right away.
So in the case where I'm trying to go to a page that's already in memory, that's the exception to the use bit. I'll go ahead and put the pointer right to that page that's in memory. I'm not going to age any of these others. Yes.
Before you have 5 at 2, right? You wanna put 5. Replace the 5 with the 2, and just go with that 5 and then just change it instead of increment.
I don't need to increment it when I go to change it if the use bit is set to 0. If the use bit was 0, I go ahead and make that swap there. It's now pointing to the oldest one, and it was 0. And then set it to 1, put the page in there, and increment the pointer. Yeah.
So we're gonna put like page 5 or 4, doing that example, it would swap out with 6.
So we want page 5. What I would do is use bit is 1, set it to 0, increment the pointer. Use bit is 1, set it to 0, increment the pointer. Use bit is 0, exactly. 5 would go in there, and set the use bit to 1, and increment the pointer. Yeah.
When you access like the same page multiple times, you just keep flipping the use bit like 0 to 1, 1 to 0, or does it go like 0, 1, 2, 3, or something like that?
Well, if it was 1 before, you're not flipping it, right? So if it was used, like my next memory reference is in page 3. Well, it's in 3, I'm not gonna change anything. Actually, it's in memory, let me take that back. It's in memory, so I don't need to do anything, other than check its use bit it's set. Yes?
If that's the case, does a pointer stay where it's at?
So pointer stays where it's at. Page fault means,
If you go out in swap spacing rather.
right, which means
There's none.
it's not in a frame. Page fault means you've already checked your frames, it's not in the frame. Everybody think they get this? Is it good?
Right, so pretty much the only time that pointer moves is when something's not in memory. You have to fault.
Right.
Page fault.
Page fault's generated because it's not in memory, it's not in a frame, and so we run that algorithm.
what's like a practical data structure to implement this? Like, I mean, do these things have to be contiguous in memory every time? Like, I mean, I was thinking maybe like, I mean, like access time, you have to like hash it almost like an object thing. I was just wondering from like a curiosity standpoint.
Yeah, so typically, there's debates about the optimal way to implement the clock algorithm, because basically it's a specialized paging algorithm for, at least recently used. So but since we're only concerned about two values, right? Since we're only concerned about two values, sometimes what we'll do is we'll just make up a bitmap and a bitmap and a pointer.
Makes sense.
Other questions? Clock. Yes?
Let's say it's like that right now, and then you want to access 2, do you need to increment it to 1?
If I need to access 2,
Do you need to increment the 0?
so if it's already in here, all I will do is set its bit.
Oh, you,
And increment the
I
point.
do want to set its bit because I just accessed it.
Yeah, that's what I meant.
Yeah.
Increment
But I'm not running the page fault algorithm. It's part of the page fault algorithm, but there was no page fault, but it wasn't accessed. So I want to make sure that every time I act, and that's how we handle it, is that, when we go to access a specific page, we're checking our page frame table. Is it in a frame? Yes, set its bit. Don't increment its bit. That's the big difference between some of the other LRU algorithms, is we're not incrementing the bit, we're just simply setting it. So if it was 1 before, we'll set it to 1 again, because it's more efficient to just set it, do the check and see if it was set, if we knew that it was already in the frame. Does that make sense? Yeah.
so you said, every time you access any of those objects, you have to change the bit to, like if you want to access 7, you just set the bit to 1?
Then I would set its bit to 1. And every time I access 7, I'd set its bit to 1.
If it's already in 1? Or, that means
I don't care. It's cheaper than doing an if, 1, then set.
So when we set the bit to 2, do we still have to increment the pointer, or no? Because it was.
Was there a
0.
page fault or not?
No. So only when it's a page fault.
So whenever there's a page fault, then I've got to worry about aging it, setting it to 0. So page fault, let's see, access the page, it's in memory, set its bit. Access a page, it's not in memory, run the full page fault algorithm. Check the pointer's current position, is the use bit set? Not, then you're right where you want to be. You kick that one out. Of course, kicking it out means checking its dirty bit to see if you have to do it right. Correct? If the dirty bit's set, you got to do it right first, and then you can kick 1 out, put 3 in, set the bit, and increment the pointer. And if it was a 1, you'd simply set it to 0, increment the pointer, repeat. Is it a 1? Yes. Set it to 0, increment the pointer, until you get a 0.
Every time you insert the new number of the page that is not there,
Mhm.
you will set all the bits to 0, right?
No. It's only setting up to 0 if its use bit was set when it was searching. Right? I'm searched. We put 3 in here. Right? Use bit was 0, so I kick 1 out. I put 3 in. I set its use bit to 1. I increment the pointer.
Oh,
I am now done. 3 is there. Everybody's happy. Until I want to access page 6. Yeah? In 6, use bit is 1. So I simply set it to 0, increment the pointer. Use bit is 1. Set it to 0, increment the pointer. Use bit is 0, I've got a winner or a loser, depending on how you think about it. I kick 7 out, I put 6 in, I then set its use bit to 1, and increment the pointer.
Why did you replace why did you replace the 7 with the 6? When you selected the 6, what you have to?
Because its use bit was 0, which meant it was a hold. My pointer was pointing to this frame, this page in this frame, and its use bit was 0, which means it had been passed over before. Because when you pass over one, you set it to 0,
Yeah.
which means it's older.
Oh.
Yeah. I know, that part's not always obvious. That's why I wanted to spend a little time on this, because that's the kind of the tricky part with this algorithm. All right? So that's clock algorithm. That's how it notionally works. Of course, we don't implement it this way in code, but that's how you can understand how it works. Okay? And yeah, we spent some time over preconditioning because in all of these algorithms, understand when you first start up your operating system, all frames are empty. You start loading the operating system in, you're going to put some memory resident pages into frames, you're going to lock those frames. And then you're going to start running so that you can start loading up your own application code and doing other work besides operating system work. Okay, then you're populating still empty frames. And then at some point, you've filled up all the available frames and you start making these page requests for pages that aren't in memory, and that's when you start generating page faults. Now it's important to keep this in mind because our community is so divided on how to approach this problem. But bear in mind that this code is running over and over and over again, and most of the time it's running after the system's been initialized. We do not want to have any special cases in our page replacement algorithms. Special case, if you just started the system, and you've got all of these empty frames, which you're never going to see once you filled up the first set. You don't want extra conditionality code on code that's running millions of times per second. There was a question here first.
I know it was previous to what I asked you before.
Yeah.
When you insert the 6 on one of those pages, wasn't the 1 and 2 also the bit set to 0? You couldn't put the 6 for J?
So based upon where the pointer is. You start where the pointer is.
Oh, okay.
Yeah.
This is a really extreme edge case, but what happens if all the use bits are 1? Means that it means
Just like our initial condition, our post-initial condition, after I filled up all of our frames, remember they were all set to 1 at that point.
Yeah.
I start wherever the pointer is.
Oh, you just go from there.
And you just go from there. We know where this is going to end up. Right. But we'll just keep doing that logic. Is it 1? Set it to 0, increment the pointer. Oh, we now have a 0. We know we're going to come back here. But I don't want a special case.
Yeah. I mean, that'd be like an extreme, probably, like almost never.
Well, it'll happen once.
Well, yeah, the first time, yeah.
Yeah. But after that initial condition, you'll never see that again. Well, no, you still could. You could get old ones. You can get those cases every once in a while.
Well, yeah, if you choose like frame 7 or something.
Yeah, you come down here, and so I zero them all out, I'm playing to here. I can come here, use that, and then use this
Actually,
again.
that should happen frequently. Like you said, you can use a small number of pages,
Yes.
Yeah.
so it's gonna happen all the time.
So I'm gonna set these all to 1, and I'll just go around again. It's okay. It's more efficient than special cases. So I bring this up because when we start doing our analysis of algorithms, some people are very adamant that you don't count those initial pages that you're populating as page faults. And I say, why create a special case? It was a page fault. Okay, obviously, the best algorithm in the world, in this case here, is gonna generate at a minimum 5 page faults, isn't it? Okay, well that means the worst algorithm is gonna generate 5 plus n page faults. I'm okay with that. I'm okay with that. That's better than saying, let's not start counting page faults until I've had my first 5. No, no. Just use the same logic over and over again from the very beginning, you're gonna get the right answer. You start creating special cases, something might get messed up. Yeah? Everybody knows what that means? Other questions?
What does that mean?
Keep it simple, stupid.
Is there a problem between simple and stupid?
Well, some people replace the last S with other words, but I won't go there. It's silly, of course, right? That's what everybody's thinking of, yeah. Other questions? No? Okay, and let's go, oh, I forgot I did put that. I like my diagram better. But you have this in your slides, so now you can follow a slightly different example of what we just talked about. Let's take a break because I want to spend a lot of time on this next slide. So let's go ahead and do a 10-minute break, come back at 12 after or so.